Let me start with the short synopsis. Immobilization of glucose oxidase, or GOD, was accomplished on pH-responsive polyimide polyacrylic acid smart gating membranes fabricated using 248 nanometer krypton fluoride excimer laser for drug delivery to improve the therapeutic efficiency in diabetic patients. GOD enzymatically converts glucose into gluconic acid, which decreases its pH in its vicinity, helping the pH-responsive membrane release a drug corresponding to the amount of glucose present. In our work, GOD enzyme was immobilized. GOD enzyme was immobilized on the membrane using a carboimide-based amidation method. The polyacrylic acid grafted inside the pores shows pH-responsive gating. The immobilized GOD molecules show glucose sensitivity as the glucose is converted into gluconic acid and the pH is reduced. After the addition of glucose, solute permeation increases almost linearly. Diffusion coefficient increases with increasing amount of glucose, which corresponds to decreasing pH. Thus, our membranes can detect the amount of glucose and release the corresponding amount of solute molecules, which in this case is insulin. So the motivation for these types of membranes, which are typically using polymeric film carriers, are used often for water purification, battery applications, and drug delivery, which is the current application. For the last several years, we have been working on a project where temperature and pH responsiveness have been obtained with these membranes. The pH response is, for the current work, is between 3 and 7. So this corresponds well to the variation of pH in the human body, as shown on this right diagram. The application, of course, relates to diabetes, which is a serious health concern for a large number of people. And currently, this problem is handled by insulin injection. However, there are often problems with poor patient compliance and poor control of blood glucose level. So our approach to remedying this problem is the glucose-sensitive membranes used in conjunction with a drug reservoir so that we can release the drug in a controlled fashion. And as I mentioned, this is done by immobilizing the glucose oxidase, and which converts the glucose into gluconic acid, thus reducing the pH, which is sensed by our membrane. The sensing is done by the hydrogel, which is grafted inside the pores in the membrane, and this occurs by the hydrogen bonds forming for the deswelling, for the swelling action when the gates are closed, and when these bonds are inactivated, the gates are opened and the solute transport starts. So in our case, the permeability coefficient, the permeability is high at low pH level when there is deswelling occurring in the pores. And as the pH goes high onto 7 range, then the swelling occurs and the gate is closed, and therefore permeability is low. So we can see that the membrane has a self-regulatory action and responds to the changes in the glucose level. The fabrication of the membrane is done by using krypton fluoride 248 nanometer excimer laser in 2 steps. In the first step, we ablate the polyimide film for providing the pores. And in the second stage, the same laser is used to graft the polyacrylic acid into these pores for the gating action. We prefer to have a Fickian diffusion through these pores so that a gating action can be achieved. The advantages of the membranes that we fabricate are the following. They are organic solvent-free, contrary to many of the current methods of membrane production, which are shown here. We obtain uniform and regular pore size and shape, and we obtain uniformly distributed pores. And thus, we avoid chemical involvement during fabrication. The other currently used membrane fabrication techniques, which are listed here, phase inversion, electrospinning, stretching, track etching, etc., unfortunately do not provide these advantages, especially in the form of preparation of uniform and regular pores, which are distributed uniformly. In the first step, we use laser ablation to provide the pores. And of course, laser ablation is a well-known technique that has been used for a long time by UV lasers. And in this case, the etching occurs either by photochemical ablation or photothermal ablation. Polyimide is able to ablate through the photochemical method. This provides us with a cleaner ablation and cleaner pore structure, in contrast to photothermal ablation, which involves additional molten material flow and other problems with the providing of high amount of heat. So the system is krypton fluoride laser. The base membrane is polyimide, which is biocompatible, has good chemical resistance, and can be ablated photochemically. Polyimide is already used in, for example, in heart implants. It has good thermal stability and is well studied in lithographic works. The grafting material is acrylic acid, which is pH responsive, biocompatible, and should be able to polymerize using the UV radiation. Polyimide is well characterized in the literature in terms of its UV absorption characteristics, and its ablation threshold is about 35 millijoule per square centimeters. The membrane fabrication by ablation is schematically shown here. We have the polymer film shown, and on top of that we have the metal mesh, which can have different mesh sizes, different pore sizes, and that pore structure is transferred onto the film by the lithographic technique using the excimer laser light, which is shined on from the top. And as a result, we get, you can see, well ordered, well-defined pores, as shown on this SEM picture, after cleaning the film subsequent to the ablation process. This is a photo of the setup. And here I show some additional schematics for the ablation process. We use, during the ablation, we use a vacuum pump to remove the ablation products. And then the film, as I mentioned, is further cleaned by using THF to get the final product. And you can see in this SEM, the very successful ordered shape and distribution of the pores. For the proof of concept, we use a small ablation area, which has about 4 millimeter diameter. And the mesh size, of course, has an effect on the final result. Here I'm showing two different mesh sizes, 635 and 325, which correspond to 20 micron and 43 micron pore sizes, respectively. With the lower mesh sizes, we have some heat effect. As you can see, these black borders on the pores. So with the larger mesh, we have larger average pore size, of course, and we obtain cleaner edges, more uniform shape, and well-defined pores. And we also have smaller affected, heat-affected area, which produces these dark regions. These lower SEM pictures show the progression of the pore ablation as the number of pulses proceeds. The membrane is etched through and complete pores are obtained. For the second step, which involves the grafting of the polyacrylic acid, this is done by the so-called pulse laser polymerization, the schematic of which is shown here. The polymerization involves the cross-linking of the acrylic acid by methylene bisacrylamide, and the initiation of the polymerization is achieved by the photoinitiator ergacure. The polymerization is bottom-up method, so the grafting solution is at the below the film, and the later is shined from the top, and the polymer proceeds from the bottom up. Here we see a grafted film with the hydrogel acrylic acid already grafted inside the pores. And the gating here is pH responsive, and it occurs through the process that I summarize here. Carboxylic groups are protonated at low pH, which leads to the intermolecular hydrogen bonding that leads to deswelling. You can see here. So with the deswelling, these hydrogen bonds are springing the polymer chains back. So the gates are open and the solute flow occurs. At higher pH, carboxylic groups dissociate, and therefore the polymers are free to expand. So the gates are closed or close, pretty much closed. So the permeability is reduced. So you can see the experimental results corresponding to that on the upper right. At pH level of 3, you can see that the permeability is high. And as we increase the pH to 7, the permeability goes down and the gates are closed. So we can therefore get the pH responsiveness in this manner, and we have a tunable permeability. To measure the permeation behavior, we use water permeation and also small molecules by using caffeine molecules. And the setup for the permeation test is shown here. It's achieved by using the dead-end stirred cell, which is shown in this insert. The governing theory here is Hagen-Poiseuille law, which relates the geometrical parameters and the pressure gradient to the volume flux, which then can be related to the permeability coefficient by using Darcy's law. As far as the production, the manufacturing process is concerned, we need to pay attention to the parameters. And in this case, we have two sets. We have the laser parameters in terms of laser frequency and number of pulses. And we have solution parameters in the form of monomer concentration and crosslinker. I have already shown the effects of the laser parameters on the ablation part. That's for step one. We also know experimental results showed that frequency controls the process time, obviously, whether it's a fast process or slow process. And this is typically, it can vary between 1 and 25 hertz, even though our equipment goes up to 400 hertz. And increasing the number of pulses decreases permeability. This is because of the increased polymerization and cross-linking. And the number of pulses also will control the exposure time. Now for solution parameters, first let's look at the effect of number of pulses for the versus the weight of the polymer grafted in the pores. That we can measure by thermogravimetric analysis, the weight, and the governing law here is through the characteristic chain length during the polymerization, which relates to the time, what we call dark time, which is the time between the successive pulses, times the monomer concentration, times an additional constant. And you can see this is a linear equation. So it's a linear behavior which agrees with our experimental results. And as far as the number of pulses are concerned, you can see the experimental results showing us a reduction in the permeability with an increasing of number of pulses. As I mentioned, at low number of pulses, we have less polymerization and higher polymerization and cross-linking at larger number of pulses. So therefore, by increasing the number of pulses, the permeability will be decreased due to increase in polymerization. You can see that expressed, described here by this schematic. And increasing number of pulses means compact chain packing inside the pores, and thus the charge density increases, and as a result, the responsiveness also increases. Responsiveness you can see by the difference in the curves corresponding to the solid and open symbols here. So that's the response range, and that increases obviously as we increase the number of pulses. So we can therefore see the effect of increasing a number of pulses. It also increases mechanical strength because increasing cross-linking and polymerization will increase the mechanical strength of the hydrogel inside the pores, because you don't want that to be washed away during the permeation. But at the same time, it also increases the process time. Frequency, that's another controlling factor. It decreases the grafting non-uniformity, increases the mechanical strength, decreases the processing time, increases charge density, and increases responsiveness. So we can see that we can optimize this system by tuning these parameters. So as far as the solution parameters are concerned, the monomer concentration governs the amount of material grafted, and the crosslinker concentration controls the chain mobility, increases in crosslinker concentration, also decreases responsiveness and permeability. We can see here that we are increasing the monomer concentration, which are listed here, and the figure on B has higher monomer concentration than A. Therefore, we can see that the increases in monomer concentration increases degree and speed of grafting while decreasing permeability. And less number of pulses are required to achieve permeability, which you can see that by just looking at like over a horizontal line and compare the experimental data. As far as the cross-linking effect is concerned, I mentioned that again, that affects the polymerization and cross-linking. And here we have the increasing cross-linker concentration as we move to the right on these graphs. And these rectangles, the blue one represents the lower pH 3, and the yellow, the higher pH 7. So the difference between the tops of these rectangles shows us the responsiveness. So we can see that by increasing the cross-linker concentration, the responsiveness and permeability is decreasing. So we can see that we are able to exploit laser parameters and solution parameters to tune our device for the intended result. And that enables us now to go to the next step, which is the achieving glucose sensitivity by relating it to pH changes. I have already mentioned how that is done by immobilization of the glucose oxidase, and that reduces as glucose reacts with glucose oxidase, gluconic acid is produced, and that reduces the pH, which in turn then opens the gates and increases the permeability and weight diffuse. So we can clearly see from our experimental results that that gating can be successfully performed. On the lower right here, we can see the effect of glucose concentration, and as we increase the glucose concentration, again, the diffusion coefficient is increased. So we can successfully use these membranes through their characteristic pH responsiveness to detect and control glucose levels. So in conclusion, we have developed pH responsive membranes with potential application in drug delivery. And the effects of various laser parameters and solution parameters on the function of the membrane have been elucidated. And that therefore brings us to the point where we can further work on optimizing our device and work on the larger scale production of this device. I would like to acknowledge my co-author in this work, Dr. Ranuka Patel, who obtained her PhD degree on this project. This project we have been working on for several years. Dr. Ankit Tiwari and Mr. Leo Wu, they worked on thermal temperature responsiveness and the effect of membrane thickness effects. And we had other faculty collaborators at the University of Akron, and their group members also work with us. We have so far published 5 papers on the results of this project in Journal Membrane Science, European Polymer Journal, ACS, etc. And I thank you for your attention, and we'll be happy to answer any questions.